I think I'm gonna head out like 15 minutes early.
Okay.
A quiz in my next class.
Okay.
That's awesome.
Okay. Thanks for letting me know.
Yeah.
Mhm. All right, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today? Good, good. Hopefully everyone's doing well. So week 5, and so we're, I know we talk about the semester as being 15 weeks, but there's also Thanksgiving week and there's also finals week. But just based on the amount of class that or amount of lectures that we're going to have, after this week we'll reach past the 1/3 point, and so that's a big milestone. And so we're really getting old. Okay, and so the plan for this week is today we're going to have a short lecture on material properties. Okay. And so, I say short, but a lot of times these kind of end up lasting from the whole time anyway. And so, but if we end early, we end early because I don't have anything else planned. And then Wednesday we have our next ANSYS activity. Okay. And so I'm still fine tuning a little bit of it. And so I'm hoping to finish that by tomorrow, just so that you can take a look at the assignment and I can get the CAD files to you guys as well. Okay. But that's our plan for the week. Okay. And I know last week, we talked about, getting the project to you guys by the end of this week, and I still plan on doing that. And so I'm on schedule for that. I have a better idea of, what I want, of kind of formulating kind of the logistics of the project. I just kind of have to write a lot of it down. And so definitely you guys can expect to have the midterm project to you guys by the end of this week. And I'll give you about a month to work on it. And so it'll be due probably end of 10th week. Okay. And so that'll be kind of a little bit of a long-term thing. Okay. So are there any questions I can answer before we get started today? Yep. No, yeah. So for the midterm project, I'm going to give you guys the CAD geometry. And so you can almost think of it as like an activity plus. And so, my intent with the activities is, for each activity, I kind of introduce some new features and answers for you. But for the project, I kind of want you to kind of put it all together. And so for the project, there's, I'm not going to give you any kind of like explicit instructions for like the mesh and the boundary condition. I want you guys to determine that yourselves. And then I want you guys to write up the report on it. But I will provide the geometry for it, just so everyone's kind of working on the same thing. Yeah. Mm-hmm. Do you have a question? Me? Yeah. No. Oh, you're just stretching it. Sorry about that. I didn't mean to put you on this. But I thought you raised your hand. So, okay. So any other questions before we get started today? Okay, right. So let's start talking about material properties. All right. And so up to this point, we've talked about what I consider kind of the ingredients to every finite element simulation, right? And so we talked about meshing for a little bit. We talked about boundary conditions last Wednesday, right? And so the last, I would say, essential ingredient are the material properties, and these are the ones that I think most people either forget or they don't really put a lot of thought into it. But there is actually a lot of depth and a lot of complexity with the material properties. Because especially nowadays, because a lot of engineering nowadays, they're especially a lot of the cutting edge stuff, they don't use simple materials anymore, and so there's a lot more I would say composite materials, a lot more complex materials. You have things like additive manufacturing, 3D printing, that's kind of that has its own batch of material properties, and so where a lot of times when you're first learning finite elements, you don't really give a lot of thought to material properties. But I would say a lot of the cutting edge out there is thinking about how can we best model these materials in a realistic way. Okay. All right. So first, let's give some definitions to this. Okay. And so when I talk about material properties, what I talk about are the physical parameters of the material that affects how it will respond, to external stresses. Okay. Because I think, we're all familiar with the idea that there are many, many different materials out there, right? And so there's, even there's metals, there's plastics, there's non-metals, there's, things like chalk, cheese, aluminum, copper, there's so many different materials out there. And I think, intuitively, when we kind of touch and hold these materials, we can tell that they're different, right? Different materials kind of feel differently. And they also have different kind of physical characteristics as well, okay? And so, when we talk about material properties in finite elements, what we're interested in is what are the numerical, quantitative ways that we can describe it that differentiate different materials from the other ones, okay? And so that's what I refer to here as physical parameters, okay? It's because it's those numerical values, it's those physical parameters that get plugged into the governing equation, and they're going to affect ultimately the finite element result that you get, okay? And so mathematically, your physical parameter or material properties basically enter into your governing equations as modifying coefficients. Okay? Right? And so the simplest example of this would be like our stress-strain relationship, right? And so one thing that's central to linear elasticity is that we have this relationship between stress and strain, right? Okay. And the material property here that affects this solution is the Young's modulus, right? Right? And so this E right here, this is a material property, okay? Because one, obviously it affects our solution, right? And so depending on the Young's modulus, it's going to give us different values of stress for, whatever values of strain that we put in. But also it's a quality or it's a characteristic of whatever material that we're using, okay? And so if we're using aluminum, then that's going to have a certain Young's modulus. But if we change the material to like copper, then that's going to have a different Young's modulus as well, okay? And so these are, parameters that are characteristics of the material, and they affect our solution, okay? And so those are kind of the two ways that at least I think of material properties when I think of finite elements, okay? All right. And so, this is kind of as simple as it gets, right? And so, the properties of the material are kind of these numerical values, but how they enter into the equation, that's something called a material model, okay? And so we won't talk about too much about material models because that's much more of a material science thing, but I will kind of, introduce a little bit of what tools are available, okay? And so we won't get too much into material models, but material models are things like linear elasticity. They're things like anisotropic elasticity. Their plasticity is another material model. And the last one we'll go over today is hyperelasticity. Okay. And so material model is the kind of, it's basically the equations that you use to describe the material. Okay. Whereas the material properties are kind of like the numbers and the actual parameters that you plug into these equations, okay? Right. And so just as a simple example here, this whole equation right here, okay, this is the equations for linear elasticity, right? Okay, so we've talked about this, quite a bit up to this point. And so linear elasticity, that's linear elasticity as a category or as a, as an equation. This is the material model. In other words, that's basically how we're saying that, the material is going to follow this equation. Okay, that's what we call the material model. Whereas the parameter that we plug in, which is the E, that's the material property. Okay. Right, and so, I want to make that definition clear because I'm going to be using those two terms quite a bit today. And so, knowing the difference between a material model versus a material property is really important. Okay, because within ANSYS, there's lots of different material models available, and then for each model, you have to plug in the right parameters or properties to it. Okay. Any questions on this? Okay. All right. And so, the way that you usually interact with this in ANSYS is that, you're going to probably look up your material in a database, okay? Unless, you're, an alchemist or something, you're coming up with new materials, which is, pretty unlikely. A lot of times you're going to be working with materials that are out there. And so, a lot of ways that, at least finite element engineers, they use material properties is through databases. And so that's kind of what I was talking earlier, where like material properties is something that people don't really think about all that much, and so they just pick the right one from the database, and then they just kind of assume that that's that is going to work. And most of the time it will. And so I'm not going to tell you that it's not going to work. A lot of times this is a perfectly fine way to do it, but because you guys are you're taking this class and it's a graduate level course, it's always good to kind of really understand the tools that you're using and have a good, understanding of, if this material is listed as linear elastic, then we know kind of exactly how it should be. Okay. And so that's kind of the goal for this lecture. And it's kind of why I kind of saved this one for last, because it's, it's much more background info more than functional info, right? Whereas, for the meshing and the boundary condition, that I would consider that as much more functional, where, we learned a lot over the last week where like you can actually apply that in ANSYS. Okay. A lot of what we're going to learn today is kind of just going on in the background, but it's good to be aware of what's going on in the background, because after you guys leave this class, you guys are going to be basically experts in finite elements, and so you should be aware of what's going on. Okay, and so let's start with the simplest material model that we have, which is linear elasticity. Okay, the one that we've been using for our activities, and honestly, probably the one we're going to use most in this class. Okay. All right, and so the hallmark for linear elasticity, as we've talked about, more than twice already in this class, is that the relationship between stress and strain in this material is linear. Okay. And so all that means is that if you draw a graph, okay, on the one side, if you have strain, on the other side, you have stress, then the relationship looks like that, straight line. Okay. All right, and then we wrote out the equation for this on the other side. Okay. And so in 1D, we basically just have a Hooke's law, where stress is equal to the Young's modulus times this strain. All right. And so linear elasticity is I think probably the simplest material model that you can have. Okay. because in linear elasticity, or at least isotropic linear elasticity, you only really need to specify two properties. And so the first parameter, is the Young's modulus. Okay, and so it's the one that we have up there. And so typically this has the symbol E. Okay. And so what this describes is basically the slope of the stress strain curve. Stress strain curve. Okay. Right. And that's going to be different for every different material. Okay. And what this slope basically says is it tells you how well the material is at resisting deformations. Okay? Okay. And so if you have a material with a high Young's modulus, what that tells you is that it's going to take a high amount of force in order to cause it to deform. Okay. And so really strong materials, like a lot of the metals that you have, like steel, like aluminum, right? These have fairly high Young's modulus, right? But if you compare it to something soft, like maybe like Play-Doh or something like that, or string cheese, right? It doesn't take a lot of force for you to stretch string cheese, right? That's how they design it, so that you can pull it apart like that. And so those materials will have a much lower Young's modulus because they resist, they provide very little resistance to deformation. Okay. All right. Any questions on this? Okay. Okay. So that's the Young's modulus. Okay. And so the other main property that you have to specify is the Poissons ratio. Okay. And Poissons ratio is strictly a multidimensional. Okay. And so Poissons ratio never shows up in classical Hooke's law that I always do, because that Hooke's law is just for 1D. Okay. But whenever you have multidimensional elasticity, then you need the Poissons ratio. Okay. Right. And the symbol we give Poissons ratio is called a nu. Okay. And so it's this kind of fancy Greek V thing. I tried 3 times and it still looks like a V, but you guys have probably seen a nu before, right? All right, and so what the Poissons ratio measures is how much a material will deform in directions perpendicular to the load. Okay. And so I think kind of the classical example will, the Poissons ratio will basically tell you how much the material will neck or it will balloon out. Okay. And I don't think those are the official terms. And so, those are just the terms that I give it. Okay. And so the kind of the classical example is, let's say that you have a strip of material like this. Okay. And if you pull it like that, right? And so if you, what the Poissons ratio is basically going to tell you is how much, this is going to happen. Right? And so you stretch the material, naturally it's going to get longer. Okay. But because of conservation of mass, right? As the material gets longer, it also has to get thinner. Right. And so this amount of necking right here is determined by the Poissons ratio. Okay. And so Poissons ratio, because it's a ratio, it doesn't have any units. Okay? And in fact, it's expressed as a decimal usually. Like the range is between 0 and 0.5. And so if you have a Poissons ratio of 0.0, basically what this says is that there's going to be no perpendicular deformation. Okay. Okay. And the max value for Poissons ratio is going to be 0.5. And 0.5 means there's going to be lots of perpendicular deformation. Okay. And of course, that's not the technical term. That's just the Justin Professor Tran term, but that's how you can think of it. Okay. And so anytime you have an isotropic, linear elastic material, you need to make sure you specify these two properties, because otherwise, it's not going to be complete, right? And so remember when we did our antiselectivity 2, right? When we specified our aluminum 6061 material, we had to specify these exact two properties. And in that case, we looked up what the properties were in a table and we just filled that in. But ANSYS wouldn't have let us done anything if we didn't fill these two values. Okay. All right. Any questions on Poissons ratio? Okay. Okay. And so I would say those two are the essential ones, and so you have to fill those in. But there's actually a third material property that's with regards to shear. Okay. And so this is known as the shear modulus. Right? And so shear modulus has the symbol G. Okay. And so the shear modulus kind of serves the same role as the Young's modulus. Okay. And so it basically expresses how well this material will resist shear deformations. Okay. Okay. And so this is actually, another important part. Whenever you do any multi-dimensional linear elasticity, you need to specify the shear modulus, right? But you're probably wondering, activity 2, we didn't specify a shear modulus, right? We didn't plug anything in. And the reason for that is, for a linear elastic isotropic material, there is a formula that relates the shear modulus to the Young's modulus and the Poissons ratio. Okay? And so for linear isotropic materials, shear modulus is related to Young's modulus and Poisson ratio by, okay, so you have the formula, which is G is equal to E divided by 2 divided by 1 plus mu. Okay. And so ANSYS knows to do this already. Okay, and so if you input the Young's modulus and the Poisson's ratio, then ANSYS will automatically compute the shear modulus using that formula. All right, question. So in the chat, question is, how do we determine if a material is linear and isotropic? Is there a table somewhere online? No, it's a good question. And so, whether a material is linear and isotropic, it'll say so in the material data sheet. And so if you look up a certain material that you want to use, it'll tell you what the most common material model is for that. And so, that's determined by the material. And so it's not something that you can determine just by looking at the material and just saying that's linear and isotropic. The way that this is determined is usually by, a series of laboratory experiments where people characterize a material. And for the ones that, that pass the test for linear and isotropic, then they're listed as such. Yeah. Yeah. Mm-hmm. Yeah, it gets difficult when you're using materials that don't have a lot of data out there. And so this is becoming more and more common with, where people are, 3D printing a lot more stuff. And so, not all of those materials, they either don't have data sheets or, the data sheets for those can be hard to find. And so that's usually when things get a little bit more difficult. But if you're using I would say more classical, material, then there should be a lot of data out there. So for most metals, you're going to find material out there. For all the common woods, you're going to have material out there. A lot of common plastics, there's going to be some place out there too. But yeah, in a world which has a lot of composite materials and new manufacturing techniques, it's getting a little bit harder, but you can also make some educated guess as well. Yeah. All right. Any questions on shear modulus here? Okay. All right. So one quick comment is that I find it kind of hilarious that the two other properties that we've looked at, they clearly have someone's names attached to them, right? And so someone named Young discovered the Young's modulus, someone named Poisson discovered the Poisson's ratio. And so whoever discovered shear, unless their name actually is Shear, but I would highly doubt that, they were either very modest and they didn't put their name on it, or it was also discovered by Young, and that you can't have two Young's moduli. And so he said, I'll call this something more that makes sense. But I always find it funny, when scientists are very narcissistic people, and so they always try to name things after themselves so people don't forget them. But I think people either just don't care about them anyway, because you look at the Young's modulus and you use it every day, but you don't give a shit who Young was, whoever discovered it, right? But he attached his name to it. So anyway, that's my rant over. Yeah. Okay. All right. So let's talk a bit about what isotropic means, because that's an important point. Okay. Okay. And so what does isotropic mean, right? And so isotropic basically means that no matter which direction that you load the material in, it's going to produce basically the same strength, okay? And so basically what this means is that the strength of the material is the same in whichever direction that you load it, okay? And so if you have a cube of isotropic material, so I'll draw the cube in 3 different configurations. Okay. Right, and so the strength of the material, or basically the strain that you experience, maybe not the direction of the strain, but the absolute amount of deformation that you see is going to be the same, no matter if maybe you load it in this direction, okay, if you load it in this direction, or if you load it in this direction, right? In all those cases, because the strength of the materials are the same on all those directions, you're going to get the same amount of relative strain, okay? And so this is actually really useful because, because if it weren't for isotropicness, isotropicity, then, you have to really pay attention to which direction that the loading is coming from versus, some other features of these materials, right? And so, I actually thought we'd talk about it next, but, this is especially important for materials that have things like fibers that are running through, right? And so the most common example of that is wood, right? And so wood, came from a living tree at some point in its life. And so, the tree has these fibers that run through the tree, right? And so the direction of those fibers, change its strength in different directions, right? And so if you load things in kind of the same way as the fiber, it's going to be really strong. But if you go in different directions, then it's going to be not as strong, okay? And we'll talk a little bit later about how we model that. But first, I want to talk about plasticity. All right. And so, talking, kind of staying on the topic of linear elastic materials, right? We know that the stress strain relationship starts out like this, right? Starts out like a linear line. But, hopefully you guys remember from your strength and materials class that once you get past a certain point, or once the strain kind of exceeds the plastic limit, the stress strain relationship is going to change. Okay? And so instead of being a nice line like that, it's going to start to kind of flatten out a little bit like that. Okay. And so the idea with plasticity is that once you kind of reach past this limit, then the material is never going to go back to its original resting position. Okay. Because normally, if you stay within this this plastic limit right here, if you load the material, okay, and so let's say that you load a material up to this point right here, okay, right, and so you apply some stress and you get some strain in the material. If you release that load, if you release that stress, okay, as long as you're still within that linear region, then what's going to happen is that stress is just going to, or that strain is just going to turn right back to where it came from. Okay. And so if you load a material, you stay within the linear limit, and then you unload it, it comes right back to where it was before. Okay. But if you go past that limit, okay, and so let's say that you load a material and it follows the stress strain relationship, okay, and so let's say that you end up somewhere over here, okay, and so you basically you exceed the plastic limit, okay, and you get this amount of deformation. Okay? If you unload this deformation, what's going to happen is that from here, it's going to be released, right? And so you're going to release the stress from it, the loading. Okay? But instead of returning to the original form, which was at the origin, you're going to, be at a state where there's going to be some strain that's left over. Okay. Right. And so this difference here, or this difference between these two points, this is known as plastic strain. Okay. And plastic strain will always occur whenever the strains exceed the plastic limit. And so this, let me use a different color. This limit here, where the stress strain relationship is no longer linear, this point is called the plastic or the elastic limit, sorry. Okay. And so a lot of times you're gonna observe plastic behavior whenever you have inductile materials that are subjected to large deformations. Okay. Right. And so if you have plasticity, or if you have plastic deformation that's occurring in your model, you need to make sure you explicitly include that in ANSYS. Okay. And so if you think back to activity 2, right? So when we specify the material properties for that aluminum, and so as it was, that aluminum is not equipped to do any kind of plastic deformation, because the only material properties that we assigned to it was those for isotropic linear elasticity. And so if you wanted to, if you wanted ANSYS to account for plastic behavior, you have to manually include those properties within ANSYS. And I believe we talked about it later. Actually, I'm gonna skip around a little bit. Okay. Any questions on this? Okay. Okay. And so this graph, you guys have seen it before in a strength of materials class, okay? But this is only relevant for 1D stresses strip, right? But in ANSYS, in finite elements, oftentimes we're working with 3D, 2D or 3D models, okay? And so in those situations, how does ANSYS determine whether you've exceeded the plastic limit? Okay? And so in those situations, what you use is the equivalent stress, okay? which we've seen before. Okay? Okay. Or another name for the equivalent stress is the von Mises stress. Okay. Again, named after the dudes that discovered it, I guess. I don't know if he's related to the supermarket, but it's possible. All right, so the formula for the von Mises stress is square root of 1/2 sigma xx minus sigma yy. Okay, so these are the normal stresses in the x and y direction squared plus sigma xx minus sigma zz squared, okay, plus sigma zz minus sigma xx. And I think there's unfortunately I don't have it written down, but there's also more contributions here from the shear stresses as well. Okay. But I think we have the formula for von Mises stress in a previous set of notes too. Okay. Oh, these papers are out of order. That's why. I wondered. I was like, why am I doing stuff out of order? Okay. All right. And so let me get organized for a second. Because in in a lot of materials, or whenever you specify plastic behavior in a material, you also have to specify how the material will harden as well after plastic deformation. Okay? Okay. Right, and so what hardening refers to is how much the elastic limit will increase in a material after plastic deformation. And in ANSYS, you have two different options available to you, which I'll go over on the next page. Okay. Okay. Any questions on this? Okay. And so the two options for plastic hardening is you can either have kinematic hardening. And so in kinematic hardening, what this assumes that the difference between the tensile stress, the tensile yield strength, and the compressive yield strength stays the same. Okay. Okay. Right, and the other option for this is compress or isotropic hardening. And so in isotropic hardening, what this does is it assumes that the tensile yield strength and the compressive yield strength have the same magnitude. And so this is important because after after plastic deformation, then the then the elastic limit is going to go up, right? And so whether the the tensile yield strength or the compressive yield strength stay the same or different, is determined by this. Okay. And so if you're not sure, I would say kind of the default or the default option you should choose is isotropic hardening. Okay. Because that's pretty simple, right? And so in isotropic hardening, what happens is that if the elastic limit goes up, then what it's saying is that in most cases, it's going to be tensile, right? And so if the tensile elastic limit goes up, then the compressive, elastic limit will also go up. And so they're going to be the same in magnitude, okay? And so if you're not sure what to pick, I would go with this one just because it's, it's a little bit easier to interpret, okay? But if you have a material which has, that has different properties in compression and tension, and so one particular material that does this is bones in your body, okay? And so bones in your body are much stronger in compression than they are in tension, okay? And so if you know that your material has a certain property like that, then that might be a good one to use kinematic hardening for, okay? But for most cases, I would say for most metals and things like that, I think isotropic hardening is a little bit easier to do. Okay. All right. And so that's one thing that you have to specify in ANSYS, right? And so in ANSYS, when you specify plasticity, you have to specify what kind of hardening behavior that you expect. Okay. And the other thing that you have to specify in ANSYS is how the shape of the stress strain curve change. Okay. And so this one you also have two options for, okay? And so the first option is known as bilinear. Okay. And so in bilinear stress strain, what you assume is that once you've reached the elastic limit, then the stress strain relationship just becomes another linear line. Okay. Albeit, the linear line that you get here has a lower slope than the previous one. Okay. Okay. And so, the bilinear stress strain relationship is a lot easier to, specify just because it's, you only have to specify the slope of another line. Okay. And so I'll draw what that looks like on the next page. But before we get there, are there any questions on this? Okay. All right. And so if you chose the bilinear option, your stress strain relationship would look like this. Okay. And so it'll look linear up to a certain point. Okay. And so this is the linear elasticity zone that that you're probably familiar with. And then after it reaches this point, it'll just become another linear line just like that. Okay. And so in the bilinear one, what you would have to specify is the slope of this line. So I'll call this the new slope. And so that's the simplest one because that's the least amount of data that you have to put in. But it's also the most crude one, right? Because I think, For most plastic deformation that you guys have seen, the relationship looks something like this, right? Looks more curved. And so if you try to approximate that with a straight line, it's never gonna be perfect. But it's a nice kind of simple way to do it. And so the other way that you can define the plastic stress strain is through a multilinear approach. Okay. And so in a multilinear approach, what you're doing here is you're specifying basically multiple lines or multiple data points in the plastic region. Okay. And so a multilinear curve might look like the following. Right? So you usually have your linear region, okay? And then your plastic region is determined by all these small lines. Okay? Right, and so this is going to give you a more accurate, stress-strain relationship. Okay? And so this obviously, is much more preferable if you want a more accurate simulation, but you would need more data points for this. And sometimes you have them available for you, and sometimes you don't, right? And so I'd say this is pretty common if you work at a company who it might have its own kind of proprietary internal material, and so they'll have stress-strain relationship data like this. Okay. And so all that you would have to do is you just have to input that data kind of forcibly into ANSYS. Okay. But if you're looking up a material like online, it might not have data like this. I've seen some out there that's open source, but it's not as common. Okay. Okay. Any questions on this? Okay. All right. And so I apologize. I know that was kind of jumping around a little bit just because my note papers here are out of order. But let's jump back a little bit and talk about isotropic versus anisotropic. And so remember when we were talking about isotropic earlier today, what we were saying is that the strength of the material is the same in no matter which direction that you're moving, right? And so not all materials are like that. Okay. And so you're going to have a lot more complex materials out there. Okay. Okay. And two of the more common ones that I want to talk about are orthotropic material models versus anisotropic material models. Okay. Okay. So let's talk about orthotropic first. Okay. And so orthotropic material models these are great when you can directly specify the strengths in each of the cardinal directions. Okay. And so if you can describe the strength in, the X direction and the Y direction and the Z direction, this works great. Okay. And so one example where orthotropic is used commonly to describe the material properties is for wood. Okay. Remember, with wood, we talked about earlier, is that they have a very distinct fiber that runs down the length of the wood. Okay, and the wood is going to be a lot stronger in that direction than it is in the other ones. Okay, and so if you're working with wood in your finite element simulation, you can arrange the wood such that the fiber runs in either the X direction, the Y direction, or the Z direction, and then you can assign different strengths to those to those directions. Okay. I hesitate a little bit to say this because I don't know if it's standard, but I would think that this is often this is also commonly used for 3D printed materials too, right? And so if you have additive manufacturing, a lot of material properties depend on which direction that you're printing the material, right? And so with 3D printed stuff, a lot of times those are built in layers, okay? And so whichever direction you're kind of building it up in, that direction is usually going to be weaker than the other directions. And so in those situations, you would have kind of the opposite, where you would specify the directions, say this is the printing direction. And so I'm going to have less strength in that direction because that's the direction where stuff gets layered on top of each other. Okay. Okay. And so for orthotropic materials, these require more material properties. Okay. Because if you think back to when we were describing our isotropic materials, we only had two material properties that we had to specify, right? So we only had to specify the Young's modulus and the Poissons ratio, okay? Because we basically assumed that it was the same in every single direction. And so for an orthotropic material, you actually have 9 material properties that you have to specify. Okay. And so it's a lot more. And so, choosing an orthotropic material, like you have to be prepared to specify those material properties. Okay. And so it's, it is a decent amount more. Okay. All right. And so that's an orthotropic material. Okay. And so I would say, out of the non-isotropic materials, I'd say orthotropic is probably the most common. Just because in those situations, like you have a direction that you can specify, and you can specify different materials in those directions. But if you want to go, completely general, and so no assumptions on the material model at all, then what you end up with is completely anisotropic material. Because even in orthotropic, right? Even in orthotropic, and we're specifying different strengths in different directions, we're still making some assumptions and we're still making some symmetry arguments about how that material is behaving. For anisotropic, we make no assumptions at all. Okay. And so this is the most general case. And so you're going to have to specify more than 9 material properties. Okay? Does anyone want to guess about how many material properties you have to specify for an anisotropic material?
27.
You looked at the notes. It's 27. Yeah. So it's a lot. And so, honestly, I can't even think of an anisotropic material that's practically used. It's much more of a theoretical kind of marvel, I guess. And so in theory, you can have a material that behaves so weirdly that you would need an anisotropic one. But in most practical cases, you're not going to get this. And so, I think in the notes, what I said is that, only the most weirdest, strangest biological materials, like say you have some kind of active components in your materials, like maybe cells or something that's causing weird stuff to happen, or maybe some very complex composite, those might be anisotropic materials. But practically speaking, at least personally for me, I've never worked with one. But in the case where you don't want to make any assumptions on the material, you can use this. But 27 is usually a crazy amount of material properties, and a lot of those material properties don't have that strong of a physical intuition. You would basically just be plugging it exactly as it was from like a research paper, which is not a bad place to be, but also not a great place, because then you're kind of blindly trusting numbers that you got from the internet, which is not the best thing to do when you're doing finite element research. Okay. And so just like I mentioned before, that even if you're working with an orthotropic material, a lot of times these are properties that have been studied before, and so they'll have published data out there. It's just up to you to find that published data and then use it in your simulations. Okay, so any questions on this stuff? Okay. All right, and so there's one more material model that I want to go over, and that's hyperelasticity. So hyperelasticity is kind of, compared to everything that we talked about today, is a little bit of a black sheep, because it kind of takes a different approach to modeling the material. And honestly, this is something that I would personally like to learn more about. And so I kind of know the basics of, just kind of working with it. I worked with it before in my research, but kind of the finer details of, how these actually came about and a lot of the derivations, I've personally never seen before. And so, I will say that I'm not the biggest expert on this stuff, but the concept is really interesting. Okay. And so hyperelasticity, this is kind of a more general, it's a more general framework or more general material model that you can use to model large deformations. Okay. All right. Because up to this point, and this is true for even orthotropic and anisotropic materials, we basically had this relationship between stress and strain, right? And so we said that the stress is algebraically related to strain, right? And so I know before that we had the Hooke's law for the simple 1D case, but in a in a most general case for anisotropic materials, you're going to have something like this. Okay? And so what you have here is basically an algebraic relationship between stress and strain. Okay. And so this is not hyperelasticity. This is everything that we've been doing up to this point. Okay. And so this is one way to define. And so this is, for linear elasticity, orthotropic, anisotropic, basically the relationship between stress and strain is algebraic. Okay. And so hyperelasticity says that, let's form a relationship between stress and strain that's not linear. Okay. Okay. And so the way that hyperelasticity works is that it uses something called a strain energy function. Okay. And it uses this to define the relationship between stress and strain. Because what you can do basically is you can take the derivative of the strain energy function, and then that will give you, how stress and strain are related. Okay? As for what the strain energy function is, okay, basically the strain energy function states that the material has a certain amount of potential energy. Okay. Okay. Right. And that this potential energy it tries to be conserved as the object goes through different deformation states. Okay. Right. And so this is a little bit of a different approach to stress and strain. Okay. And so for each deformation state, basically what you're looking for is the minimum of the stress energy or strain energy function. Okay. And so mathematically what's going on underneath the hood is that when you apply an external load, then the strain energy function is computed, and then its derivative is taken, and then it tries to find the deformation configuration that minimizes that strain energy. Okay. And I wish I could explain it a little bit better than that, but that's kind of the limit to how I kind of understand it. Okay. But basically what this allows is that it allows for very non-linear stress strain relationships. Non-linear, and I would say very complex. And so, we looked at a little bit of non-linearity already with plastic deformation, but hyperelasticity, you can get really crazy stress strain curves. And so the downside of hyperelasticity is that it assumes no plastic deformation will take place. And it often requires you to read some kind of academic papers just to understand what it's actually doing. And so it's the difficulty for hyperelasticity is a lot higher, but the potential is there for a lot of really interesting deformations. And for some materials, they're honestly just best described with a hyperelastic material model versus a linear one. Okay. Okay. Any questions on this so far? Okay. All right. So one example of a stress strain relationship you can get with hyperelasticity looks something like this. Okay. And so you might get something that looks, something crazy like that, which, as you can see, this is impossible to get with, a normal linear elastic material with even plastic deformation, because you can see that we have a transformation from like a kind of linear zone up into like a plastic-ish zone, and then suddenly it's jumping up again, right? And so this would not be possible with a linear elastic model with plastic deformation. Okay, this is only possible with hyperelasticity. And some materials, actually behave like this, right? And so just to give you an example, so a lot of my in my past life, I did a lot of research on blood flow, right? And so part of that research is modeling how the blood vessels themselves, like the walls of the physical blood vessels, how they deform in response to, the pressure changes in your blood, right? And so it's a lot of research has shown that blood vessels, they're not a linear material. They actually follow a stress strain curve that may not look exactly like this, but you can't fit a linear curve to it. And so, I have a little bit of experience using these kinds of models, but it's not easy. And so I was kind of in that position where, like, the software that I was using had some hyperelastic material models to it, and then I was just kind of using it and plugging in values. And so I think I got interesting results, but at the same time, I don't think I fully understood it, which is not a great place that you want to be in, especially when you're presenting it for your dissertation. Okay. And so I would say the main difficulty with using hyperelastic material models is that there's a lot out there. Okay. Okay. Because the whole idea with hyperelasticity, it's almost like a way of life. And so there's not a specific hyperelastic model. Hyperelasticity is kind of like a framework. And so this idea of having a strain energy function for your material is just an idea. And so what different researchers have done is that they've proposed different strain energy functions. Okay. And then each of those strain energy functions will be used for certain things. Okay. And so the reason there's lots of different hyperelastic models is lots of people have proposed different strain energy functions. And so I used two when I was in grad school. But when I looked up hyperelasticity in ANSYS, I was actually in for a little bit of a shell shock, because if you look at the list of all the hyperelasticity material models in ANSYS, it's a long list, and like I don't even recognize most of the stuff in there. And so I'll give you some examples. Okay. And the unfortunate thing with hyperelasticity is the same problem that we encountered before, is that whoever came up with these strain energy functions just named them after themselves. And so the names of these mean absolutely nothing. And so one example is the one that I've worked with is the Neo-Hookean model. Okay. And so ANSYS has this one. I've seen it. Okay. Another one that I've worked with is called the St. Venant-Kirchhoff model. Right? So you remember St. Venant from before? I guess he worked with Kirchhoff and he developed this strain energy function. Okay. And another one I know is popular for biological tissue is called the Mooney-Rivlin model. And I believe this one is these two are also in ANSYS as well. Yeah, so those are common. And of course, you read those and you have no idea what they mean because they're named after people, and no one cares about the people. We just want to use your equations. And so, it's one thing where, you kind of have to do your research into what material you're using and what material model makes the most sense. Or I would say what material model people have used and kind of read their justifications for why they use that for that material. And then you can use the same thing. Okay. All right. Any final questions on this before we wrap up for today? Okay, all right, so that's material properties. And so, I think for most people, with finite elements, you don't really think about it a lot, but the rabbit hole goes really deep with material models, especially when you start talking about hyperelasticity. All right, and so on Wednesday, we're going to be doing our next ANSYS activity. And so, have workbench ready for that. But besides that, thank you guys for coming today. Hope you guys enjoy the rest of your evening, and I'll see you guys on Wednesday. Yep.
I was wondering if you can take a look at the activity we just turned in.
Sure.
Question about this information.
Sure. Yep.
I think I did list this in one of my answers, but I had an incredibly large deformation here, and I think it's because I fixed it incorrectly. But I had fixed it for on this surface here and the opposing surface.
Yeah.
At the top, or sorry, at the bottom right here.
Yeah.
And then I applied I think it was, last time I checked, it was a component force.
Yeah, 150
Yeah,
pounds.
over here I applied a vector force
Okay.
straight down.
That shouldn't matter too much because the deformation is localized right there.
Uh-huh.
That must be from the 150 pounds.
You know, there's a surface here that's like obviously like parallel to the rest of this, right? That's where I applied the load. I think it might have ended up being like a shear on that surface of the load. Is what I'm thinking. I mean, 677.
That is a lot of deformation.
It's a bit ridiculous. So I was questioning.
The only thing I would say is that maybe check the units one more time. Although it seems like you're in the right units, but this is in inches,
right.
and so the force would be in pounds. The only other thing I would check is just make sure that the material is aluminum, because that would be the other thing that would cause the smartest deformation. Because the loading on this one wasn't that complex. Like we basically just had a few fixed supports. I mean, it looks like you fixed it just fine, and it wouldn't cause that.
Right
huge
there,
deformation.
right there. I think you had shown, or when what you had shown in the activity was it was just fixed here, or did you show that it was fixed on the other side as well?
It was supposed to, it was supposed to be fixed on both sides. I think with the angle of my screenshot, it might have been like one. But,
Yeah.
but it's right that you fixed on both sides.
Right. Okay, well, I guess I'll double check those things. The only thing I'm thinking is that I might have not applied the force here on the right surface, because technically it's supposed to be normal right here, right?
Yeah, it's supposed to be in the y negative y.
Negative y direction.
Yeah.
Yeah, I'm pretty sure I did that.
Yeah, so that's the only thing I could think, because usually when the deformations are this high, usually it's material model or units are kind of those are the only things.
I initially saw that, I'm like, there's no way that's correct. But yeah, I mean, I don't know if you read through these, but I think I listed off what I thought it could be.
I did see that. Yeah, it was a little bit strange. That was kind of like almost like an extra question, and so I didn't read. I was mostly focusing on the crank part. This is something I just added, just this year. Just because one
spent more time on this one.
Oh, really?
Because I was like really frustrated on what was going wrong with it.
Yeah, because one feedback I've gotten from the finite elements over the years, like the activities I think are okay, but I think everyone just wants a little bit more practice of applying what we've learned in different geometries. And so like what I've done before is every activity there's just kind of one geometry, and so in every activity is something new, right? And so this was kind of like my first attempt to say let me try to give you something new.
No, it's cool because it's a real.
Yeah. But because of that, I haven't done extensive testing on this one as I have on the bike crank, and so I'm really not sure what
Okay, I'll double check units, material properties, and maybe get back to you from there.
Okay, just double check those things and just let me know. If you still can't figure it out, then we can run through it again on Wednesday and then see from there.
Yeah, I mean, I don't think it's a meshing issue.
I don't think so, no, because everyone's using the same mesh, because you use the 0.4 inches.
Yeah.
And this looks good to me, like the way that this is meshed. So
okay.
But yeah, just
I'll
double
do a
check
little
those things,
troubleshooting
and
then.
then let me know if you find anything.
All right.
Yep.
Thanks.
Yep.
Professor, actually, I ended up running my frame simulation again.
Yeah.
And that spot on the tube went away. I don't know why.
I
just redid it.
It
went away.
Yes, I remember because I set mine up the same as you did, and I didn't get that spot on the thing either. Honestly, it's probably like a meshing, because that model that I gave you guys was not designed for FP, and so that was strictly just a CAD model.
Okay.
And so kind of like we talked about before, like there's those sharp angles, and those are really dependent on how the mesher decides to mesh across those things.
Okay.
And so if you mesh the same object twice, even with the same settings, you're not going to get the exact same mesh.
Okay.
And so it could be you just reran it and the mesh is just a little bit shallow. That's the only thing.
And then, so I have a question. So I'm about to finish up the biomechanics paper right now. And so in one of the papers, one of the main like factors to determine, so basically the way that this lady set up her study is she took a bunch of female college runners who had tibial stress fractures before.
Yeah.
And a bunch who didn't, right? And so when she was doing her analysis, like the most statistically significant indicator was that women who had previously had tibial stretch fractures had a really high tibial acceleration, or like PPA, which was the acronym, but partial something or other. And so she said it was like the beginning of, she basically said she removed the linearity from the graph or something like that to determine what the tibial acceleration was. So she basically saying she took the derivative of one of her measurements. That's what she said. She
Okay.
says I'm asking you, because I don't know, when she says like I removed the linearity,
Oh,
what does that mean?
usually when they say that, then they're using a different equation for that.
Oh,
And so a lot of times, like a lot of like, especially dynamics equations are pretty complex, like they have it on a non-linear shape like that.
okay.
And so normally it's really hard
Yeah, I
to
looked it
find
up.
that
It's
relationship.
like,
Yeah, normally it's really hard to find a relationship between inputs and outputs.
okay,
And so a lot of times you kind of have to assume that it's a linear shape.
okay,
But by doing that, you kind of lose some information too. So probably when she said she's removing the linearity, she's probably saying that, let me assume that maybe the relationship is quadratic or maybe exponential or something like that. So
okay.
I'm guessing she's probably doing a different fit to a curve than just linear.
Okay.
That's what I'm guessing.
Yeah, because I was like trying to look up in her literature, like, okay, what does this even mean? Like, I guess peak tibial acceleration, I guess it's like when you come off the ground or something like
I
that.
see.
How fast. But like, she never really specifies that very well. So,
That's the important thing with papers, that they
Yeah.
assume their audience knows all those things. But
yeah, and it's like, how am I supposed to learn? this? You know, like, I'm not- So I've been like kind of looking it up, but it's so specific that nobody really does a very good job of explaining it.
And
They
some people,
explain one of the other variables pretty well, but not this one, unfortunately.
sometimes people call things different things too. So she might be calling it like tibial acceleration, but maybe someone calls it something different, which is really annoying. But
Yeah, because like what I'm trying to do is like that. So I did the running surfaces one, and
Yeah.
that study has nothing to do with running surfaces. But it's like interesting because like different running surfaces like change your leg geometry.
oh yeah,
So like, you know, I guess with softer surfaces, your legs are much stiffer
Mhm.
because they have to compensate
Yes.
for the softness of to like maintain speed and all that
Yeah.
stuff. So your body does it naturally, I guess.
Yeah.
And then with the concrete, you have a lot more knee flexion. And I thought that was interesting because I believe she said that a reduction in knee flexion, I mean, it's not statistically significant technically, but there was like a trend of people who suffer from stress fractures, they had less knee flexion.
Mhm.
So, you know, that could mean that running on grass might not be ideal for people who have had tibial stress fractures.
Mhm.
But I think the most important thing was that acceleration off the concrete.
Yeah.
And apparently you get increased acceleration off off your step when you're on a harder surface.
Interesting.
But then I saw another study that was like people with tighter legs get bone injuries more often. So, you know, if you're running on grass and your leg is tighter, that means that your bone has to absorb more of the impact. So I don't know. It's like I don't even know what to say. Like in my conclusion, in my introduction, I just put that surface selection is going to have to be athlete specific, like based on their. And then in my conclusion, I'll probably just try to say some of the same thing, and that the research isn't conclusive on whether or not you should run on soft or hard surfaces.
Those are always hard, and so for those situations, like I always tell people, just present the data that you have, and present what you found in the literature, and then just what makes the most sense to you. Because each of those studies, like they're going to have different data, and they're going to have different explanations for that. And so just whatever makes the most sense to you. So these are the data that we found, but in my opinion, I think this one makes the most sense.
Okay.
But just put it all out there and then just kind of give your interpretation and opinion.
Okay, I'll do that. I'll do that in my discussion.
Sounds good.
Section.
Sounds good.
All right, thanks, Chris.
Yeah,
I'll be right back. Are you leaving right now?
I need to talk to Ian first, but then, but yeah, I'll probably leave after that.
Okay.
Hey, just one quick question.
Yeah.
What's the importance between by picking between isotropic and kinetic pattern?
Yeah, so that's the main difference for that is because I would say that's more of a difference for dynamic situations. And so for dynamic situations, you're gonna have like, you're gonna load the material and unload it, you're gonna load it and unload it. And so that basically determines like when you unload it, how much stronger is it going to be. And I'll be honest that I don't have the most experience with that. I've only just kind of just learned about it in theory. And so I'm not sure what people practically choose out there in the industry for situations where they experience that a lot. But it is a choice, but I included it because, if you look up and you try to include plasticity enhances, that's something that you have to choose. And so for me, the one that makes the most sense is isotropic, just because you kind of keeps both of them the same. But whether you choose kinematic or isotropic, it really depends. It's material specific. And so my impression has always been that if you kind of expect that you have different behavior in compression versus tension, and so for sure that it's going to be stronger in tension versus compression, then maybe kinematic one makes the most sense, because then you kind of preserve that relationship where become more tensile and compressive. But if you don't have any data that suggests that they're different, then isotropic makes no sense on that. But that's just my own kind of personal conjecture, kind of just based on what I've read. I don't know what they actually do with it. So but I think it'd be an interesting point to say we do work for someone that does this stuff, and just kind of ask that question.
So in the past census activities, we didn't apply this because we do not need to unload.
Exactly. Exactly. We also didn't have any classic deformation at all. So we assume that all the deformation that we've had so far is purely elastic. And so we're just sticking in that linear region. And so if we do unload it, we just come right back to where
So yeah, I read your email. I think I'm not entirely sure about the difference between the two applications.
Okay.
But just listening to the sound, I think I would go for the engineering
Okay.
side. And I recall that I've read maybe one or two papers that try to optimize the method of the simulation by finding out which parameters should be set of paramount importance.
Yeah.
Something like that. So from my understanding, the engineering side of application will be going into this direction.
Yes. Yeah. No, you're exactly right. And so if you are interested in that, I do have a project that that someone just finished, or he didn't really. Well, he got as far as he could, but the data we got from it wasn't that great. And so I can just describe it really quick to you, and then I'll ask him. Let me close the Zoom.
Yeah, sure.
Let me make sure that there's no one here. Questions. Okay, good.